Yeah, greetings, my people. Welcome to today's presentation. In today's class, we are going to look into the topic functional group. So by the time we'll be done with this class, we should be able to define a functional group, give examples of these functional groups and the family they belong to, and the possible reactions they are involved in. So let's look at the definition of functional group. It said that the functional group are seen as the most reactive parts in organic compounds and equally determines the major properties of the compounds. So what we call functional groups are those parts of the organic compound that are very reactive. When we mean by reactive, that they are involved, they take part in the reaction. In fact, the reaction occurs at this point. So this functional group could be they could be an element or a group of compounds, but they are the sensitive part of that compound, and they equally give or determines the name or the family of that compound. So the functional group, apart from being the most reactive part of an organic compound, they also determine the family of that compound. I would want us to look at these reactions. You will see how functional groups is being attacked. For a reaction to take place, forming a new compound. If you look at the first one we have there, in the first reaction, that's halogenation, you will see that halogenation, of course, is the addition of a halogen, which in this case, the halogen we have in this case is bromine. The addition of halogen in this case, which is bromine, to an alkene compound. When the reaction takes place, you can be seeing the reactions on the screen. When the reaction takes place, you will notice that the functional group in alkene, which is a carbon-to-carbon double bond, has been attacked by the bromine molecule, breaking one of the bond to attach itself. So the bromine here will break one of the double bonds, which is the functional group for alkenes. When it breaks one of the double bond, it will now attach itself to the compound, forming a saturated compound. That is, if you look at the reactions, you will see that on the left-hand side, we have our alkene, which is ethylene in that case, and we also have our bromine. When the bromine attacks, or when the reaction takes place, at our right-hand side, you will see a new compound that is being formed. And in that new compound, you notice that the bromine has attacked the double bond, which is the functional group in alkene, attaching itself and giving us a saturated compound, which is 1,2-dibromo-18. 1,2-dibromo-18. Now, let's look at the structures very well. If you look at it very well, you will notice that we will still have double carbons as in ethylene as well as in ethane. We equally have 2 hydrogen each on each of the carbon atoms. In the left, that is ethylene, and in the right. But the only difference here is that in the left, which is ethylene, we have double bond. But in the right-hand side, which is the new compound that is formed, we have only single bond with an attachment of bromine. That is to say that the bromine has reacted with the double bond by breaking one of the bond, then attaching itself to the compound, forming a saturated compound, which in this case is 1,2-dibromo-18. So the essence of this reaction is to tell you how functional groups react. What we mean by they are the most reactive part of a compound. So you can see that carbon-to-carbon double bond has been altered as a result of the attack or the reaction of bromine on it. Then, in the same way, what happens in the second reaction when an ethanoic acid reacts with an alkanol to form an alkanoate and water? you see that is what happened is the same thing that happens in the first example we give, the first reaction, which is halogenation. The point of attack in this reaction is the functional group. If you look at the left-hand side, we have two compounds there. We have the ethanoic acid and we have the ethanol. In the ethanoic acid, we have the functional group as COOH. COOH, if you look very well, you'll see that after CH3, the next C has O and OH attached to it. This O and OH is the functional group for alkanoic acid. Then if you look at the other compound, we have CH3, CH2, OH. That OH is the functional group for alkanols. So you see that if you look at these two compounds, you see that we have the COOH as the functional group for alkanoic acid, and the OH as the functional group for alkanols. Then if you look at the compound formed, it's a reversible reaction. The arrow there shows that it's a reversible reaction. That is, it can go either ways. If you look at the reaction, the product, you will see that we still have our CH3C, O up. Then if you come down, our oxygen now is a hydrogen is being eliminated from the OH, attaching CH2, CH3. The hydrogen that is left in our ethanoic acid reacts with the OH, which is remaining in our ethanoic acid, ethanol, to give us water, that is H2O. So the main reason for this reaction, like I said earlier, is to see the point of attack or the point of reaction. So you see that the point of reaction in these two examples are the functional group. So when you have COOH, you notice that the CH3C still remains, but the attack was on the COOH. That was where we had the changes. The same thing happened in CH3CH2 OH. You notice that at the end of the case, the functional groups were what was missing or not complete, if I should use that word, because what we now have, we have an additional compound which is different in functional group. The functional group is now different. The functional group we had earlier is not the functional group we are having at the product side. So you see that the point of attack in this case is equally at the functional group. So when we say that the functional group is the most reactive part, this is what we mean by the most reactive part. The most reactive part is that part that is open for reaction, for attack, for defense, if I should use common words, English words to explain that. Now, for us to understand more about this functional group, let's look at an analogy of a functional group. For a more and a detailed understanding of a functional group, let us liken it to the things we are very familiar with and see how we can draw our understanding of functional group from there. Let us look at the functional group as a family name. Let us look at it as a family name, for instance. It is a name that identifies you from a crowd. For instance, if in my own case, my name is Austine, then my family name or surname or last name, as the case may be, is AZC. AZC is what now differentiates me from every other Ifeanyi, Austine, or a male child or a man, whichever, in any way you could see it. So that AZC, which is my surname or last name, is a name that classifies me as a member of that family. The same thing happens in a functional group. A particular functional group classifies or limits a compound to a particular family. Now, for let's go further. In terms of reactivity now. In terms of reactivity, the functional group is likened to the active parts of a human body, like the arms, the legs, etc. The arms and legs interact with our environment in many ways, such as defense, attack, acceptance, etc. In functional group, these elements or atoms, that is, which are the functional groups, interact more with the environment in terms of chemical reactivity, forming different products. So I'm trying to liken this functional group with something we are very much familiar with. I'm trying to see if there's a way I could draw conclusion between the functional group and what we are very familiar with. So I'm using the human body to see if I can get you understand more deeply what we mean by the functional group. So if you take the hand, for instance, you will see that there's nothing that is being achieved as a human that your hands are not involved or your legs are not involved. For a work to be done, your hands and legs must be actively involved. For you to create something, something a physical, you must involve your hand. So your hand is always the point of contact between you and the environment. So in the same way, in a functional group, a functional group is a point of contact between the compound and the environment, and is that's what we say is the reactive part, is the part that is open for reactivity. So whatever that comes, where it's going to hit first, is at the functional group. So the functional group now defines or determines the kind of reaction that is going to happen. If it's something that is compatible, they form a reaction. If it is not, the reaction is not, and there won't be a reaction formed. So the most reactive part of a compound is what we call the functional group. In human beings, we liken it to the hands and the legs. There are many parts of the human beings you can liken the functional group based on its functional activity, but we're using the hands and the legs here for easy understanding of what I mean by functional group. So the hands and legs are to the human bodies what functional groups are to organic compound. So there are some examples of these functional groups and their structures which I would want us to look at. The first one I want us to look at is the alkanes. Alkanes. These are carbon to carbon single bonds. The functional group of alkane is the single bond. Alkane. So if you look at the structure we have here, you see that we have C, that is the carbon, linking to the other carbon with a single bond. And we have other attachments which could attach other elements, but the functional group in alkane here is the carbon to carbon single bond. Then we can have an example of alkane as the one we have in this slide. We have the ethane. Ethane. You will see, if you look at the compound very well, the ethane compound, you will see that the carbon to carbon single bond is what is holding that compound. So is the root of that compound, the ethane. So the alkane has carbon to carbon single bond as the functional group, and reactivity, the single bond also defines or determines the kind of reaction that will occur in a compound. So anytime you see a carbon to carbon single bond, it automatically tells you that that compound belongs to a family of organic compounds which we call the alkanes. That is why I likened functional group with family name or last name. So if you have so and so last name, that means you are associated to. So sometimes our last name even try to tell people where we are coming from. So in functional groups, the alkanes, the functional group also tells you where a particular compound belongs. So when you see carbon to carbon single bond, that automatically tells you that this compound belongs to a family of group we call alkane. And for them to belong to alkane, that functional group has already given you an insight of the kind of reaction this compound should undergo. Let's look at the second one, which is the alkenes. The alkenes is similar with the alkenes, but the only difference is that the functional group here is the carbon to carbon double bond. In the reactivity example we gave, we used the alkene to react with bromine. We saw what happened in the reactions. So in alkenes, we have the functional group as the carbon to carbon double bond. And an example of this compound, a compound with this functional group, is the 18. If you look at 18 very well, you will see that it's of almost the same. It's the same with the 18, except that the 18 has a single bond, while the 18 has double bond. So if you look at this compound, or any compound that has carbon to carbon double bond, automatically that double bond, because of that, the presence of that double bond, carbon to carbon double bond, which is a functional group, it will now tell you that this compound is an alkene compound. And when you are naming an organic compound, you take note of the functional groups, so that you know how to name them. Because when you are naming an organic compound, you name it in such a way that the naming will align with the family name, which in this case is the alkene. So if I should name a compound that contains double bond, I will make sure that the double bond is shown or pronounced in that in the naming. And not only shown, but the position of the double bond will equally be shown. If you look at my lessons on the naming of organic compounds, you will understand this very well. So we've seen the first functional group of alkane, carbon to carbon double single bond, and this one is for alkenes, carbon to carbon double bond. Let's look at alkynes. Alkynes has a functional group of carbon to carbon triple bond. Is of the same. Is almost they are of the same nature. Let me use that word, nature, because in the first one we have single bond, the second one we have double bond. In this case, we have triple bond. Now, in this triple bond, whatever that is happening to this compound in terms of reactivity, it affects the bonds. It takes one, and when you remove one out of the three bond, we have double bond. That means we are leaving the alkenes family to the alkanes. So when you see a carbon to carbon triple bond, then we are referring to the alkenes functional group. An example of the alkene functional group is what we have here in our structure. If you look at the compound very well, you'll see that we have 4 carbon atoms bonded with a single bond, except one which has triple bonds between the carbon and the carbon. And because of the presence of that triple bond, we will now be able to say that this compound belongs to the alkynes family. And because it belongs to the alkynes family, we treat it as one. Then if we are talking about reactivity, for instance, the reaction or whatever happens to this compound will now affect the functional group. The reaction will be on the carbon to carbon triple bond. So in the example we have here, what we have now is but1 ion. But1 ion. But because we have 4 carbon atoms. 1 because the triple bond is between carbon number 1 and carbon number 2. Ion is now telling us that this compound belongs to a family of organic compound, the alkynes. So this is the functional group for alkynes. Let's look at the other functional group. Let's look at for alcohols. You can call it alcohols or you call it alkanols. The functional group for this alcohol is the ROH. The ROH. The OH actually is the functional group. The R is now the organic compound that is attached to the component, the functional group. In this case, the R could be an alkyl compound. An alkyl, what we mean by alkyl is when we have CH3, CH2, and rest. Then array, if we have a ring, a benzene ring attached to that functional group. So the R is a hydrocarbon. Let me use the word hydrocarbon to classify it. Then the OH is now the functional group. So in the alcohols, we have the OH as the functional group. So whenever you have a compound with OH attached to it, it now tells you that this compound is an alcohol or an alkanol, as the case may be. So let's look at an example. you can look at this example. You can see that we still have our OH, but our R is being replaced by CH3. If you look at the carbon very well, you see that it's attached by 3 hydrogens, but we still have our OH. So what it means now is that we are replacing our R in the functional group with CH3. That is now giving us methanol. Now, the met, because we have 1 carbon atom, then the nol, because this 1 carbon atom is a compound which belongs to a family of organic compound in alkanols or alkanas. So the functional group has already told us that this compound belongs to a particular group, which we took note of when naming this compound as the methanol. So you can see that the functional group equally gives us the surface name of a compound. So if you look at the alkyne we see that we have both 1 ion. The ion as the functional group is telling us that the function is the compound is of the alkynes group. If you look at this one, we have the methanol, and the methanol is telling us that this compound is of alkanol family. Let's look at another example, which is the carboxyl group. If you look at the carboxyl group, the functional group for carboxyl group is this RCOOH. RCOOH. So the colored COOH is the functional group, while the R is a hydrocarbon, like I explained in the case of alkanols. So the COOH is the functional group, then the R is the hydrocarbon. So when you have COOH as a functional group, you will now classify that compound as a carboxyl group. Let's look at an example of this compound. If you look at the compound we have there, you will see that we have 3 carbon atoms, and one of the carbon atoms is being attached by that OOH, giving it the COOH functional group. So if we look at the 2 structures very well, the one up is our functional group, which is the carboxyl functional group, RCOOH. Now, looking at that RCOOH, let's now try to see how it has something to do with the second one, which is the propanoic acid. Now, if you look from the right, extreme right, you will see that we still have our COOH there. Then our R, as in the case of the functional group, is being replaced by CC, that is double carbon and hydrogens. The C, which is normally the C is an eth, that is double carbon, ethane, whatever. But because we have to consider the carbon on the functional group, we now have total in this compound, we have 3 carbon atoms. And because we have 3 carbon atoms, and our functional group here is telling us that this compound belongs to the carboxyl group, we now name this compound as propanoic acid. Remember, the carboxylic acid is the alkanoic, and the carboxylic group is the alkanoic acid. And because it's the alkanoic acid, we name taking cognizance of that parent name. So we now call this one propanoic. Propa because we have 3 carbon atoms. Noic because it belongs to the carboxyl functional group, carboxyl acid. Now let's look at the carbonyl group. If you look at the carbonyl group, the difference between the carbonyl group and the carboxyl group is the carbonyl group we have CO as the functional group, but in the carboxylic carboxyl group we have COOH. The carbonyl has CO. Let's look at an example. If you look at the example we have, the image we have, you see that we have our carbonyl group and we have R. R could be C. What we mean by C is carbon or anything else, as I explained earlier. Let's say that our R is a hydrocarbon. So if you look at the first structure down, you see that we have RCOH. Now, when we have RCOH, that is, we have our carboxyl attached to the carbon atom that has the functional group CO, then the functional group is attached to hydrogen. In such a case, we call that compound an aldehyde. They are an aldehyde because the carbon that is holding the oxygen, that is the carbon-oxygen functional group of carbonyl group, is attached to a hydrocarbon, which is R, and a hydrogen. Then we call such compound aldehyde. But when we have our carbon to oxygen functional group of carbonyl group attached to R, which is a hydrocarbon, and attached to R again, which is hydrocarbon, we call them ketones. But both of them, both aldehydes and ketones, are all carbonyl groups. They belong to the same family, just that the carbon holding the oxygen in the functional group in one is attached to a hydrocarbon and a hydrogen, while in the other one it is attached to a hydrocarbon and a hydrocarbon. That's the difference in those ones. So let's look at the two, should I say, compounds or family compound that is formed under carbonyl groups. We have the aldehyde. In the case of aldehyde, let's look at the first structure. There we have the formaldehyde. In the formaldehyde, we have CO, which is our functional group. Look at the C double bond oxygen. When it is being attached to hydrogens, two hydrogens, we have it as formaldehyde. Then if you look at the second compound there, you can see that our C double bond O, which is our functional group, is being attached to CH3 and hydrogen. Then that one is equally an aldehyde. If you look at the two remaining compounds there, you'll see that the carbon holding oxygen must attach with at least one hydrogen for it to be an aldehyde. The carbon holding the oxygen must attach to at least one hydrogen for it to be an aldehyde. Then if you look at the ketone part of it, you'll see that the ketone has the carbon attached to oxygen, or rather the carbon holding the oxygen, that is our functional group here, CO, is attached to R and R. There's no hydrogen here. In the first case, which is the acetone, we have it attached to CH3 and CH3. So, and in the second one, we equally have it to attach to a ring, a benzene ring, and the CH3. So you discover that the difference between the aldehyde and the ketones is that in one, there must be hydrogen attached to the carbon holding the oxygen, while in the other one, there is no hydrogen at all. That's the only difference. But the functional group remains the same, which is COCO, linked with a double bond. So that is for the carbonyl groups. Now, there is this group we call the amino groups. The amino groups has their functional group as NH2. Then the R, of course, I've explained the R to you. The R could be an, let's say, hydrocarbons. Can be an alkane, can be an array. So it's a hydrocarbon. So, but the functional group for amino is NH2. So let's look at an examples. You can see the examples we have here. We have methylamine, dimethylamine, and trimethylamine. These compounds is trying to, show us the in our minds. In our minds, we have three amine groups. We have the primary, the secondary, and the tertiary. So the three examples of the compound with amino groups is trying to, show us the primary, secondary, and tertiary. The first one, which is methylamine, is the primary, where we have the R, which is CH3, attached to NH2. Then when we have the hydrogen attached to CH3, that is the hydrocarbon, we call it a secondary amine, which is dimethylamine. Then if you look at the third one, you see that the nitrogen is attached to three hydrocarbons, that is CH3, CH3, CH3. That is trimethylamine. All of them are amine compound. The only difference is that they belong to different class. The first one is the primary amine, which is NH2. The second one is the secondary amine, which is NH, only one H in this case, with other hydrocarbons. And the third one is the tertiary amine, N and 3 hydrocarbons. So, but all of them still fall to the family of the amino group, the amino, which is the NH2, the amino group. So, irrespective of the number of hydrogens attached to the nitrogen, yes, they all still belong to the amino group. But for simplicity, the functional group for amino groups is NH2. NH2. So anywhere you see a compound that is being attached to NH2 or any of the examples given below, you will be able to know that this compound belongs to a family of organic compounds which we call the amino group. So ester is another functional group in organic compound. Ester is similar to the arachidonic acid, except that in the COOH of the arachidonic acid, ester has COOR or COO. Let me use the word these three elements COO. We have the R. I've explained what R means and hydrocarbons. So in this functional group, we have the first R and the second R having an apostrophe. What it means that the first R and the second R might or might not be the same, but what it means that they must be a hydrocarbon for them to be considered ester. They must contain in between them COO. If you look at the example below, you will see that we have the first one. We have 4 examples here. We have ethyl propanoate, and thank God they are colored. You will see how the R's are now are in functions. The first R, which is in this first example CH3 CH2, of course you can see our COO there. Then our second R is the CH2 CH3. So you see that they are of the same, the 2 R's are the same. That is, they are both that's a double bond. But because the first R has CH3 CH2C, which is attached to the OO, we now have them as 3 carbon atoms. That is why we have the name as ethyl propanoate. So when you are naming, you first of all name the R apostrophe, the hydrocarbon that is attached on the R apostrophic side before naming before you name the one that is attached to the carbon holding the 2 oxygens. Then let's look at the second example there. You can still see or cite our functional group COO. That is in the methyl butanoate. You can still cite our COO and see how the 2 R's are taking positions. The compounds that are replacing the 2 R's. In the first one, we have CH2, then attached to our functional group. Then in the second R, we have CH3. And the same thing in all other examples. So for esters, we have the functional group as CO. Then in that CO, R, which is attaching to the C, that is holding the CO, is a hydrocarbon. Then the R, which is attaching to the one of the oxygen, is also a hydrocarbon. So in this case, when you see a compound of this nature, you will now be able to say, oh, this compound belongs to a group of organic compound ester. So that is the functional group for ester. Now, there are compounds that can have more than one functional group. It's not as if that we've exhausted all the functional groups that is in existence, but I use those ones which I gave you as an example, as a guide on what functional groups are and how to identify them and how they take part in reaction and why they are being called the most reactive part of an organic compound, and why I liken it to family name, what the hand or arms of a human being, and how their reactions resembles each other. So in some compound, we notice that you can actually have more than one functional group attached to that compound. An example is where we have the 3-hydroxybutanoic acid. 3-hydroxybutanoic acid. Now let's start our analysis with the name. The name says 3-hydroxybutanoic acid. Then we have the structure there. That hydroxyl, oxyl is telling us something, that there is a family of compound that is attached to this compound we are talking about. And that oxyl is trying to flash our mind back to the alkanols, or alkanals, that is the alcohols. Then butanoic acid is telling us that there's another functional group here, which is the alkanoic acid. Now, because a functional group, like I said, identifies the family of a compound, anywhere you see a functional group, you must indicate the family that that compound belongs to, even if they have more than one functional group, like in this case. So if you look at the name, you see that the name is telling us that this compound is a combination of two functional groups, that this compound has two functional groups attached to it. They have the hydroxyl functional group, which is the alcohol or alkanals, and they equally have the ethanoic acid. That is the carboxyl group. So that is why in naming it, we have to identify that we have the oxyl or hydroxyl, and we have the carboxyl groups. So we have the name as 3-hydroxybutanoic acid. Then we equally have another example, 2-aminopropanoic acid. 2-aminopropanoic acid. Now, 2-amino is telling you that we have an amine attached to that compound, and propanoic acid is equally telling you that we have an icanoic acid attached to that compound. So what I'm trying to say in essence is that whenever you have more than one functional group in a compound, the naming must indicate that this compound has a combination of socio-functional group and socio-functional group. So that is that. Then in the third example, we have but-3-enoic acid. But-3-enoic acid. Now that N, that is En. That En is trying to tell you that we have a double bond functional group attached to that compound, and that oic acid is equally trying to tell you that we have an alkanoic acid attached